So I welcome you all for the week 4 class on geotechnical engineering laboratory. So in this session, we are going to see about triaxial test, vein shear test, and consolidation test, and also we'll see some one or two problems how we can solve that. So regarding triaxial test, so consolidated drained test. The first thing we have to remember in consolidated drained test is your pore water pressure is going to be zero, that is your uw. Your pore water pressure is going to be zero throughout the entire process of testing. So at no point we are allowing the pore water to generate, and we are making the pore water to dissipated. So your uw is going to be zero, pore water pressure is going to be zero. So as soon you see the word consolidated drained test, you have to remember that the pore water pressure is zero. Okay, so whatever the parameters we get, okay, so like c or 5, that we call it as effective stress parameters or total stress parameters. Both are going to be same. Your total stress sigma and your sigma dash are going to be equal because your pore water pressure is zero here. So your failure envelope will look something like this, okay, where you have a c and phi in a consolidated drained test. So how, as I discussed in your last class, what we are going to do is we are going to apply the cell pressure for the consolidation stage. And for the cell, for the applied cell pressure, once all the pore water pressure is dissipated, then we do the applying the deviatory stress. So we apply the so this is our sample. So we apply the cell pressure, okay. So we apply sigma 3 and we'll wait for the consolidation to get over. Then once the consolidation is over, then we apply our deviatory stress, that is going to be sigma d. So before the start of the test, we have to know the diameter, length, and area, density, void ratio, etc. Fine. So for every, so we have a just as as we do in UCC test. Okay, so there is a plate which will be moving upwards. So for every 30 divisions, okay, so for every 30 divisions rotation, you'll be noting down what is the load. So you know what is the deformation, that is your rate of move, your plate will, so this is your sample which will be placed here, and this is the load applied. So this plate will be moving in upward, so you have a dial here. Okay, so you have a dial here. So for every 30 rotations you will be noting down what is the load. So your strain is calculated from this, that is from the change in length by original length. Original length is 76 and change in length is zero point 0.6. That is how we calculate strain. And we find the corrected area, which is nothing but original area by 1 minus epsilon. These are similar to your unconfined compression test. Okay, so for first consolidation pressure 50 kPa that we have applied, we are noting down what is the load taken by the soil, and at one point it will reach a maximum and it will fail. Okay, so the load will be keep on increasing and it will reach a maximum and it will fail. So for one corresponding cell pressure we get one deviatory stress. Okay, this is your sigma d. Then we have to remove the sample, put a new sample, and then again for a second confining pressure we again get a second deviatory stress. So your deviatory stress is nothing but load by area. So we know what is the maximum load it has attained divided by the area will give you the deviatory stress. Fine. So for every consolidation pressure, we get one maximum stress. So everywhere the concept is same. The load will be keep on increasing. You can see the load will be keep on increasing. Okay, at one point it will fail and will start decreasing. We note down what is the maximum load taken by the sample divided by the area will give you the stress. So for each corresponding cell pressure, we get a corresponding deviatory stress. Okay, so this is your deformation, strain, corrected area. For each applied cell pressure, we get a maximum deviatory stress. Fine. So here you get the maximum value here in each case. Okay, then they start, once the sample fails, when it is not able to take any more load, the load will be starting to decrease. That divided by the area will give you the stress. So you have to remember this important equation. Your sigma 1, which is a major principal stress, is nothing but sigma 3 plus sigma d. That is, if this is your sample, okay, this is your sample, all around already we have a sigma 3 all around. Okay, so this is a platform, sorry. So all around we have a sigma 3 acting during our consolidation stage. And here in this plane we are additionally applying a load, that is your deviative stress. So this becomes your major principal plane. So the total stress on this plane is going to be sigma 1, sigma 3 plus sigma d. Sigma 3 is a, already we have applied a confining pressure, and sigma d is a load that we are additionally applying. So when we are going to apply sigma d, when there is a major principal this gives you the major principal stress. Okay, fine. So we get to calculate what is sigma 1 in our each stage. Okay, the given that sigma 1 minus sigma 3, that is a deviatory stress, is 290. So sigma 1 equal to sigma 3 plus sigma d, deviatory stress. So we get your sigma d in each sorry, sigma 1, that is your sigma 1 for each confining pressure. Then we plot the Mohr Coulomb. Okay, so Mohr Coulomb circle for for unconsolidated undrained test, you get a circle of same diameter. Okay, that will once we do the test also, we'll be able to see such results only. Okay, so in an unconsolidated undrained test, this is the way where you get your Mohr circle from the results. And for consolidated drained only, you will be getting these kind of curves. Okay, fine. So this is how your triaxial test is plotted. And from the result, we get what is our Cu value. So this value will give you your Cu value. Instead of plotting the curve, we can also directly get it from a formula. Okay. So this formula, sigma 1 equal to sigma 3 yeah, sorry, sigma 3 tan square alpha, we call this as alpha, this 45 plus 5 by 2. Once again, sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. It's a very very important formula. This all our triaxial test results, mean all our numerical problems of triaxial test revolves around this formula importantly. Okay, so sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha, 2c tan alpha. These are the different methods, other ways to write this formula. So this alpha, what is this alpha? This alpha is nothing but 45 plus 5 by 2. We call this alpha as failure plane angle. So in numerical, if they give you directly what is a failure plane angle, then you directly get your angle of internal friction from this formula. Okay, so another method of writing this formula is this method, where tan square alpha is nothing but 1 plus sine phi by 1 minus sine phi, all are derived. Okay, so the root of this is going to be tan alpha. So you either use whatever suitable for you. So this formula, as I said, important for you. So in a problem, one of the numerical, okay, so they have given you a dry sand. Okay, dry sand, we have a dry sand. Okay, so dry sand is tested in a triaxial, and we are going to conduct CD test. Okay, so if it's a CD test, what is the pore water pressure? 0. And if it's a dry sand, we have to understand that your C value is 0. So in a dry sand, if sigma 1 and sigma, your deviatory stress and pore water confining stress is given, then directly you can use this formula. You can see this numerical. See, they have given that the sigma 1 is 180 and your pore water pressure is 20. Okay, for this case I'm saying. So this is a cu test, or it can be uu test, that they have not mentioned, but it's okay. So if it's a cd test means this portion will not come. Okay, so we'll consider only the sigma 1. So deviatory stresses your deviatory stress is going to be one second. So sigma 3 is 80 kilopascal and your sigma 1 is 160 kilopascal. Okay, directly we are getting your sigma 1 and sigma 3. If they have given deviatory stress, you can get your sigma 1 value from the formula that I previously told you, that is sigma 1 equal to sigma 3 plus deviatory stress. Okay, deviatory stress. Okay, so your sigma 1 is going to be 160 and your sigma 3 is 80. Okay, if it is a consolidation drained test, I told you that this u won't be coming. Okay, for example I'm explaining. So in a dry sand, if it is a consolidated drained test, we have sigma 1 and sigma 3. Then how do we find phi value? So we directly substitute in this formula, so this part will be 0. So sigma 1 equal to sigma 3 tan square alpha. If we substitute the values, we get phi value. Okay, so this is one method to solve the problem. If they have given the pore water pressure, then you have to minus the pore water pressure with all the major and minor principal stress, and you have to apply the same formula. Okay, so in both the cases, there is not much difference. If they have given the pore water pressure, you have to minus that with your sigma 3 and sigma 1. In a cd test there is no pore water pressure, so you no need to worry about that. Okay, so this is one of your model assignment question they have asked. So using this formula, sigma 1 equal to sigma 3 tan square alpha, where alpha is nothing but 45 plus 5 by 2. Fine. So next is your vein shear test. So vein shear test, we will be using vein shear test in a field. It is actually a field test in order to find out the undrained cohesion of the soil. When you are not able to collect the sample, for example, if it is going to be a soft clay means it will have a very high liquid limit. Okay, so it is very tough to procure a sample from such a stratum. So when you have a soft clay, especially when it is close to coastal regions, the clay that is closer to coastal and marine areas, it will have a very high moisture content. The liquid limit also will be closer and to the natural moisture content. So it will be very tough to get a sample from that place. So we'll be conducting a vein shear test in such areas. So we are going to do a laboratory vein shear test here. So in laboratory we are going to do a small prototype of it. So we'll be able to know how to calculate in a field similar pattern. So your vein shear test, you are going to find out the undrained shear strength of clay. That is very important. So this test is purely used or exclusively used only for clay soils, and also it should be a soft clay. Okay, the shear strength of soft clay, it is difficult to obtain and accurately in a lab by conventional triaxial. So we are using this vein shear test to determine the shear strength. Okay, similarly that we conduct in field. So what we are going to do here is, so this is what we call it as vein. Okay, so it has a four blade. Okay, this portion alone, this small thing, is what we call it as vein. Okay, it has four blades of diameter and 12 wide and 24 long. We have different varieties of very different length. So this is the laboratory vein shear apparatus. We have a small mold here. We have to fill the soil. We have to fill the soil mixed in its more than its liquid limit. Okay, we have to fill it, trim it, then we have to place it at the bottom and insert this vein. Okay, so you can see this vein is completely immersed in the soil. So we have to immerse this vein, and if you note down here, it is a graduated circular scale. Okay, so once you start the motor will be rotating. So the this vein will be rotating at a very slow rate. So these are the springs that will be fixed here. depending on the spring constant we'll have different values. So we have to choose which spring we need to use depending on the consistency and thing. So we'll be putting the soil and insert the vein and we have to start it. So this will be rotating. At one point when the soil fails, okay, there is a small needle here, it is located here now. Okay, there's a small needle, this needle it will split. Okay, that difference we have to note down the initial reading and then will get a final reading. That reading will be helpful to find out the torque that has applied, from which we'll be finding out the undrained shear strength. If you note this form, if you see this formula, here you can see. So you initial at what degree the arrow is placed, that we are noting down, and final degree. Okay, so for the we are repeating for 2 to 3 trials. So initial and final reading, so that we convert into torque. This 2.3 is nothing but spring constant. Each spring has a constant, a spring constant value, which will be given by the manufacturer. So this spring constant into pi. Okay, this will give you the torque that is applied. From the torque applied, we have to we have to find out what is the cu value. Okay, so divided by pi into d square h. D is the diameter of the vein, height of the vein. So everything in the denominator is related to the vein dimensions. So we know what is applied torque and we know what is the diameter of the vein and height of the vein. We get the undrained shear strength. So there are two things that we can get from vein shear test. One is the sensitivity of the clay. We call that a sensitivity. That is on disturbance, how easily it can lose its strength. Okay, if it is highly sensitive. Okay, if it is highly sensitive, then a slight disturbance can cause a severe shear failure. If it is less sensitive, then that disturbance is not going to cause the disturbance because of drilling or making a borehole is not going to affect much. Okay, so we get a sensitivity parameter from this vein shear test using your remolded strength and undisturbed strength. Okay, so this is what vein shear test is. It's a simple test. Just we have to fill the soil in 3 layers, tap it well, and we have to insert the vein and start the motor. So your needle will be at an initial place, and after it fails, the vein along the surface of the vein, the shear strength will be uniform. That is our assumption. So because of this rotation, we can, if you just twist it, the soil will fail soon. Okay, the rate of rotation of the vein is very very less, so it will rotate at a very slow rate, and at one point when the sample is failed, it will move to another location and there's a small split up of the arrows here. So you note down what is the initial reading, what is the final reading, and you convert them into torque by multiplying with the spring constant and pi value, and you divide it with your formula, that is your vein dimensions. Okay, it's a simple and easy test. Fine. So the next comes the consolidation test. Okay, so consolidation test, as far as clay sample is concerned, consolidation test is a very 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 important test. Okay, so consolidation, as I told you, when we have a clay soil. Okay, when we have a clay soil and when you apply a load, okay, because of the applied load, the pore water pressure gets dissipated. Okay, and there is a decrease in the thickness. So this is what we call it as delta H. Okay, so delta H it is. So this is what consolidation is. So when a saturated soil mass is loaded, the volume of voids decrease while the volume of solids and pore water pressure remains, while the volume of solids and pore water remains unchanged. Actually your Vs will remains unchanged. If you are allowing for drainage to happen, then water gets dissipated and your volume of the soil decreases. So the decrease in voids results in escape of pore water. That is important. So what it's like a, imagine it's going to be simply a, a sponge dipped in water. So you have a sponge dipped in water and you press it. Okay, your water gets coming out. Okay, why the water comes out? Because of the applied load, there is a decrease in the voids. So when the voids are coming lesser, the particles becoming closer, and the water is expelled from the soil. So that the samples are loaded to a stage until 90% consolidation is achieved. So there are some important parameters that we get from the consolidation test, which is going to be, first is going to be coefficient of compressibility, AV. We call that as AV, the ratio of change in void ratio to the change in stress. Okay. How do we calculate this change in void ratio? Everything will be, we'll see later. Okay, so these, one is coefficient of compressibility, then we call it as coefficient of volume change, which is mv. Mv is nothing but delta E by 1 plus E naught into delta sigma. This minus symbol we can ignore, it just shows that there is a decrease in the void ratio, that's why this negative symbol is used. Okay, so mv is delta E by 1 plus E naught into delta sigma. Next is your coefficient of consolidation, that is what very very important. This is what we get uh, from our I mean, this is what we need to find out from the consolidation test. See, coefficient of consolidation tells you the rate at which a soil may consolidate. If you have two different soil at two different sites, so you have a cv value, one is going to be zero point 0.8 and another cv value is going to be zero point 0.3 or something, then it shows that your cv with a zero point 0.8 will consolidate at a faster rate. Okay, so cv gives you an idea at the rate at which the soil will consolidate, the rate at which the water may dissipate. Okay, it will not give you an idea about magnitude. Two things are there in settlement, one is going to be rate of settlement, another one is going to be magnitude. Rate means with respect to time, whether it will settle fast or settle slow, and magnitude is nothing but delta H, that is whether it will settle more or settle less. Okay, so your cv value will give you an idea at rate at which it settles. This cv value also helps you in ground improvement, and everywhere it comes into play. So whenever you are going to improve the soil by stone columns or pre-consolidation, there are a lot of ground improvement methods that we adopt to improve the site with a clay soil. So when we go for such methods, we have to know whether what method we are using is going to be effective or not, whether it has worked. So how do we know? So we measure cv value before doing any ground improvement, and we measure the cv value after doing the ground improvement. So that will tell you that okay, this method has worked very well, and it has increased the rate of consolidation. Always we need the rate of consolidation to be faster. That means that the dissipation is faster, the settlement has occurred and a shorter duration, means it will if you have a clay soil of 5 meter thick in a site, imagine it gets for a you are going to propose a building there. Because of that building, it is going to settle some um, let us keep that it is going to settle some 40 or something. Okay, so they have a clay soil at a site. Okay, it is going to be around 10 meter or 15-meter clay soil, and when I'm going to construct a building there, it is going to settle for 40 okay, which is not acceptable. So what I'm going to do is I'm going to make the soil to settle by applying some load. That is not the building, but I'm going to keep some blocks. We call this as pre-consolidation. I'm going to keep some concrete blocks here, and I'm going to attain this 40 settlement before my construction of building. So once when my building is constructed after this settlement, it will not settle anymore. Okay, because it has settled already for a proposed load. So when the load is applied, when the building is going to be constructed, it will not settle more. Okay, so if I'm going to see that this 40 settlement is going to take some 1 year to happen, I'm calculating. Okay, I'm going to take some samples and I'm doing some testing, and I'm finding out that it takes settlement of 40 for 1 year. I cannot wait for 1 year. Okay, so what I will do, I will do some ground improvement methods. I will drill some boreholes, I'll put sand drains. Okay, I am introducing some new drainage paths. See, the water has to come from here to here, so it will take lot of time if it is a two-way drainage. So what I am doing, I am creating some shorter paths for them so that it will come faster. Okay, now I can attain the 40 settlement in some 3 months itself. So all these have some practical applications. Okay, so this cv value will tell you at what rate it is going to settle, and this we find out before and after doing some ground improvement methods, it will help you to know the improvement of the soil. Then comes a compression index, cc, so which is going to be change in void ratio to the change in log of sigma 1 by sigma naught. So this value again, cc, will tell you about delta h. If cc is larger, your settlement is larger. If cc is smaller for a soil, your settlement will be smaller. Okay, so that will help you, give you an idea of the settlement that may happen in a soil. Fine. So then we have pre-compression pressure, which is like, when you are see, in clay itself we have over consolidated clay and normal consolidated clay. I don't want to go into deep much. Okay, so and under consolidated clay, so these two are important: over consolidated and normally consolidated. So if you are going to subject clay soil, I mean, um, pre-compression pressure is, it is a maximum load to which an over consolidated clay was ever subjected. So for example, we have a ground here. Okay, it has clay. Okay, now it has a building of 10 floors. Okay, because of this 10 floors, now it has undergone some settlement and some change. So this 10, because of this 10 floors, it has experienced some pressure. Okay, now I am going to demolish this building. Okay, I am demolishing this building and I am going to construct a 3-floor building. So this clay will not undergo any change because of this new structure, because it has already under experienced the 10 floor pressure due to a 10 floor building. Okay, so we can call that as pre compression pressure, the maximum load to which it is ever subjected. That is what, 10 floor. Okay, so if I'm going to construct a 23 floor, now this will undergo some change in its height. Okay, because of now, because from 10 floor I have increased to 23 floors. So until I construct 10 floor, it will not undergo any change. Once I start with the 11th floor, then it is going to undergo some change. That is what we call it as this graph with a e log p curve. In a e log p curve, okay, we'll have horizontal portion here, horizontal portion, and then there is going to be a decrease in the void ratio. So this pressure here, we call that as pre consolidation pressure, sigma naught dash. That is, this is your 10 floor pressure. Okay, until you apply this 10 floor pressure, there is no change in void ratio. Once you start increase from your 11th floor, there's a decrease in the void ratio. Okay, so that is what over consolidated claim is. It has been subjected previously, it has a stress history. It has been subjected to some maximum load to which it is we call that as over consolidated clay. Okay, yeah, it all depends on the pressure. Okay, the normally consolidated, over consolidated, everything depends on OCR ratio. Okay, there is a term called as OCR ratio. You can check into that. Okay, next comes your coefficient of permeability. So as I told you, in permeability test when we studied, there are indirect methods to find out permeability. So from consolidation test, we can find out what is permeability. So it is K is nothing but CVAV into gamma W by 1 plus E naught. Okay, this is one method to calculate your permeability. Fine. So this is actually also important. Okay, just remember this formula where they will give you the coefficient of consolidation, coefficient of compressibility, then your initial void ratio, means you can find out what is the permeability of the soil. So how do we perform this consolidation test? So you have a ring here, sample ring. Okay, this is of 75 mm diameter. Okay, so you have a sample ring here, and the diameter is going to be 75 mm and the height is going to be 2 centimeter. And you have a porous stones, this we call it as porous stone. So it's a simple arrangement. So you have a outer ring. Okay, and this is your sample ring. You have to put a porous stone at the bottom, put a filter paper, place the ring with the sample. Okay, it has to be filled with the soil. Where it can be undisturbed soil, like we from directly we have taken it from the field, or it can be a remolded sample which is prepared at 1.5 times the liquid limit. Okay, you place it, put a filter paper at the top and again a porous stone, and you place this ring at the top and you lock it, seal it well. That's what. And we place our loading arrangement at the top. So you have a porous stone at the bottom, soil sample, porous stone at the top. Then you have a loading cap. This we call it as a loading cap. We put a loading cap and we place it in the frame. So this is our frame. We put it in the frame and we arrange this lever and thing to be exactly horizontal. And place a dial gauge at the top. You can see a dial gauge. So this is your loading frame and we place the weights here. Okay, we place the weights here. Fine. So initially we put a seating load, or it can be 6.25 or anything. Okay, put a seating load and you have to wait for 24 hours, then we do the test. So what we do is, initially we put a weight and we have to note down dial versus time. Okay, that reading we have to take it. So this is your table. So time, this is your time, which is going to be point 0.2 in minutes, 1 minute, 2.25 minute, 4 minute, 6.25 minute, 9 minute. Okay, so this is your time. And this is nothing but root t. Okay, we have to take root t, that is for calculation purposes. So you have to note down what is the time versus dial reading. You can see this is your dial reading for the first loading condition. So they have applied point 0.1 to point 0.2. So we have a point, we have a load increment from point 0.1 to point 0.2. Okay, load increment is done and we are noting down what is the time and dial reading for first load increment. Okay, then after 24 hours of reading, you have to increase, put the next load. Okay, and for the next load you have to note down the dial. Next load increment, next loading. So each load increment has to be twice than the before load. Okay, that is there. So generally we go in this manner. We apply 50 kPa, then 100 kPa, 200 kPa, 400 kPa, then 800 kPa. This is how we generally apply the load. Okay, so this here they have given in kilogram per centimeter square. We go in terms of kilopascal. So first we apply 50 kPa first day after your seating load. We note down what is the dial reading for different time. Okay, what is the dial reading? Then we apply one more 50. So I will put one more 50. So how much it will come? It will come to 100. Then I will note down what is the dial reading. Then I will put a 100 kPa load. Okay, 100 kilopascal. That is nothing but you have to calculate. I'm talking in terms of stress. You have to calculate the corresponding load for that area. You know what is the area of your sample. For 100 kilopascal of stress, you have to calculate what is the load. Okay, that divided by 10 you have to put usually. Okay, why? Because this lever arrangement, if you see, it was like a load into this area. Sorry, this distance. Okay, that we have to consider. So whatever directly the load what we are applying, it will be multiplied into this distance. We generally keep this as 10. So whatever load you are putting, it will be multiplied into 10 and that times it will be applied. That is the reason for this load increment. Or else we will not be able to load to a larger amount, because it will be if imagine if there is no load lever here, then if you are loading from the top, then you have to load, you have to take large amount of load to generate that stress. But because of this arrangement, just by keeping some lesser load, you can arrive at a larger stress because of this lever arrangement. So whatever load you are applying here, it will be getting multiplied with the distance. Generally we keep this as 10, as I said. So 10 times the load what you apply here will come here. So this load by area you have to calculate and you divide it with the distance from the lever to the center of the sample. Fine. So this will give you 200 kPa, then 400 kPa, 800 kPa. This is how we apply the stress and we get whatever the dial reading versus time we will be plotting. Fine. Then once we complete to 800, okay, when once we reach 800, what we do is we do the unloading. That is, just like we cannot remove all the loads suddenly. Okay, so we do the unloading. So we remove the load for there. Here you can see the 30 minutes time frame is followed. So first 400 kPa is removed, then 200 kps removed, then 100 kps removed for for 30 minutes duration. You have noted down the time. Okay, unloading just some one or two reading is enough. So how do we do the calculation? So we have to note down, we have to get what is the, what we are going to plot is E versus log of P. This is what we are going to plot. Okay, so for each load, that stress, that is 50, 100, 200, we need to find out what is the void ratio. Okay, so that is what we are going to find out. So ultimately, so specific gravity, height of sample, area of the sample. We know what is the height. We know what is the area. Okay. Then we have a dry mass of the sample. We will be finding out after placing this in oven. Once the test is over, once the unloading is done, take the sample, keep for water content, and and also find out what is the dry weight of the sample. Okay. So height of solids, you have to find out what is height of solids, that is nothing but Vs by A, volume of solids by area. So what is this volume of solids? Volume of solids is nothing but, you can see here, your G is nothing but unit weight of solids by unit weight of water, gamma S by gamma W, I can tell. Okay, so your gamma S by gamma W is your G value generally. So from gamma S, which is nothing but unit weight, weight by volume, so weight of solids by volume of solids into gamma W. So from this we get Vs, volume of solids, which is nothing but Ms into Gs gamma W. So we are trying to get what is Vs, volume of solids. Your volume of solids is mass of dry mass of solids divided by G into gamma W. In this, all the factors we know. So your dry weight divided by 2.7, that is 145 into divided by 2.75 into area. Okay, we are taking your gamma W or rho W as 1. That's why it is not there. Okay, why rho W is not there is, everything is in centimeter we are measuring. So your rho W is nothing but 1 gram per cc. Okay, so this is in grams and this is in cc, centimeters. So we are putting rho W as 1 gram per cc. So that's why we get 145 by G into A, which will give you the height of solids. So initial height of voids. How do we get the initial height of voids? So we know what is your initial height of the sample minus your height of, that is nothing but see, your total height of the soil. Total height of the soil is height of solids plus height of voids. If you have soil here, if you remember your three phase diagram, okay, so this is your solids and this is your void. So this is nothing but height of solids, which is not going to change. Whatever the consolidation what we are going to is related to the height of voids. So from here you can see that your total height is nothing but HV plus HS. From here we are getting HV. HV is total height minus HS. So your void ratio, next comes your void ratio. So your void ratio is nothing but height of voids divided by height of solids. Your E naught, initial void ratio, is HV by, you know that your void ratio, what is void ratio? Volume of voids by volume of solids. We know that volume is nothing but area of voids into area, you can put area into height of voids divided by area into height of solids. So this area is same, area of the soil is same, diameter of the soil is not going to change, only the height is getting changed. That's why your E naught, your initial void ratio, is nothing but HV by HS. Your initial height of voids divided by the initial height of solids, that is nothing, sorry, HS, that is nothing but 11.94. Okay, so this is not going to change. Always you have to remember that your HS is a constant parameter, it will not change at any point of the testing, because solid is not your solid particle, they are not going to undergo any change. Whatever the stress that you are going to apply is going to be reflected in the voids, the void is getting decreased, whereas the solids are remaining unchanged. Okay, fine. So your next set of calculations will come. So you are noting down what is the load applied, and you have to note down what is the final dial reading for each increment of load. So for each load you are noting down what is the final dial reading. Here for example it is 16 mm. Okay, next you have to note down what is the compression. Your compression is from the initial height. uh, that is when you set your dial at 0. When you start your test 0, you are noting down. If it is going, your dial reading shows some reading means you have to note down. Okay, so your compression is this value. Okay, next your height of voids. For each increment you have to find out void ratio. As I said, for each increment you have to find out void ratio. So your height of voids is hv equal to this 13.06. That is your initial value. You can see a 13.06 minus 4 point minus 0.431. Okay, the change in dial reading. So this is going to be your height of voids 12.629. This 12.629 divided by here you are. Okay, fine. This is what I was searching. Okay, so you are noting down the initial reading, final reading. This is at 0. Okay, so this difference will give you the compression. And you are noting down for 0.431. Then height of voids is nothing but 13.06 is your initial void ratio. Initial void ratio from 13.06 it has decreased to 12.629. Your voids have been decreased to 12.629. Now what is your void ratio? Void ratio is, as I said, 12.629 divided by 11.94. That is your height of solids. I told you height of solids will not change. So for every decrement in void ratio, divide it with 11.94. You'll be able to find out what is the change in void ratio. So 1.05, the void ratio has come, and this my difference will give you how much void ratio change has happened. And you know what is del sigma, this difference. Okay, so you calculate what is av and mv from direct formula. Okay, you calculate what is av and mv, and you plot your e log p curve. E log versus, there is in a semi log, in a semi log graph. Okay, so this is going to be log scale and this is in normal scale. V versus log of, okay, we put as log of p. Okay, we put it in a log 50, 100, 150, and we plot it what is the void ratio. And from there we get the slope of this is going to be your compression curve, and this is going to be your recompression curve, I mean unloading curve. This is your loading and this is your unloading curve. The slope of this curve, the slope of loading curve, okay, is your cc value. You find out what is the slope. You can see here, so this will give you 0.265 from c. Any small test in consolidation, we can relate the cv value, the cc value that you find from the uh, test is going to be constant even in for a field soil. That's why it is very important, I said. So we get the value and we can calculate the settlement, what that can happen in the field. Okay, so we have to find out CV value. As I told, CV value, we have two different methods. One is called as log T method. The other one is called as root T method. Okay. So first we'll see how to do log T method. So for one particular stress value, we can plot it. In general, it is going to be constant for all. Okay. So we know what is time versus, I can show here. This is your time and this is your dial reading. Sorry, this is your time and this is your dial reading. Delta H is your dial reading and this is your time. You get a neat s curve like this from your this is in log scale. Okay, so this is log t, as I said. So this will be in log scale, log graph actually. Okay, um as I said, it is a log graph. So you get a neat curve like this when we plot it. What you have to do is you have to choose 2 points, p and q, on the curve. Okay, you have to choose 2 points. For example, if p is going to be 0.25, you have to choose that, we have to multiply that with 4. Okay, so 4 into 0.25 is 1. Okay, so you have to point, find, choose any point on the curve as closer to the initial reading. So I have chosen first p point, and that is going to be some 0.25 minutes. Multiply that with 4 and you can find get q point. Okay, so we get 2 points. You measure what is the distance between the 2 points, measure them. Okay, then plot the same distance on the above p. Okay, so these you have to first find out what is this. For example, this is going to be some 1 centimeter. Just from this line, plot again 1 centimeter from here. Okay, you get this point. This what we call it as u0. We call this as u0. Then for this curve, you have to do a double tangent method. That is, you have draw a tangent like this and draw another tangent like this. Okay, this is straight portion. Okay, so you do it looks like a tangent for this curve. So you connect this straight portion and this straight portion, you get a some point here. So this we call it as u100. Okay, so u0 and you call it as u100. And in bit you measure what is the, you find out what is the midpoint. For example, this is the midpoint. If I'm telling this as u50. Okay, so this you uh, project it to the x-axis. So this is what t50 we get. T50 from log this log t method. Okay, so once you get this T50, that is time for 50% consolidation. We call this as time for 50% consolidation. So you know what is T50 now. Okay, now you know what is the thickness of the sample. Then you can find out what is the CV value. This is 0.97 is time factor for a 50% consolidation, which is a constant. So 0.197 h square by T50. So how do we find? We choose point P, which is going to be at some time t of 0.25 minutes or something. Multiply with 4, we get point Q. Measure the distance. For the same distance, you plot it at the top and you project it in this axis. You get u0. Then you draw two lines, okay, such that the straight portion of these curves are connected. Then you connect it. So this is your u100. Okay, so you get u0, u100. Mark the midpoint, that is u50. Then you get your t50. Okay, that is how we find out t50 from the graph. And we find out what is the CV value. You can see a d100 they have put. This is d0. Okay, and this is d0 plus d100 by 2, the total length by 2 you have to find out. And when you project it to the y axis, x axis, this is your t50. Okay, fine. So next is going to be root t method. Okay, so for root t method, you have to plot it in a normal graph. Okay, you plot the graph. Root of time, you can see root of time. That's why we take in this manner. If you note down the first method, first time when we note down the time, this is the time we take. We simply convert into root t, means we get a whole number. That's why we note down the, these are constant. For this time only we'll be noting down the reading. Okay, so when we convert into root of time, it is a whole number. That's why we always follow this time thing. Okay, so we get a normal scale. In a normal scale, if you plot a graph, root of time versus dial reading in a normal graph. Okay, fine. Sorry, for log t method, you have to use a semi-log graph. This is a semi-log graph. Okay, I said it's a log. Sorry, it's a semi-log graph. Okay, fine. This is a normal graph. Normal, our standard graph. Root of time versus dial. You get this curve. Okay, you get a curve like this. So what you have to do is, you have to this straight portion of the curve, you have to project it backwards and you have to mark r0, this straight portion. Okay, you have to mark it r0 and you have to extend it from axis. You have to note down at which point, at how much distance this x is. For example, imagine this x is 1 centimeter. So this distance is 1 centimeter. Multiply with 1.15. Okay, multiply with 1.15. So from here, take 1.15 and mark this point. Okay, you have to mark a point here. Yeah, you can see here 0.15x. So the total is 1.15. Okay, so just the straight portion you extend it, and you extend in the downward and measure how much is the distance. Then multiply that x value with 1.15. You mark a point from here to here, mark a point at 1.15. Now you connect this point and your r0. Okay, it will cut the curve at a somewhere it will cut the curve that you project it downwards. That is your x-axis, which is going to be root of t90. You have to square it, square the time, that will give you t90. You can see this is a formula to find out cv value from root t method. Approximately both the methods should give the same cv value. Okay, so 0.848 h square by t90. Your t90 should be squared of this. That many times we make a mistake. Okay, whatever we are finding is a root of t90 here. Square it and we find out what is the t90. From that we get what is the cv value. Okay, coefficient of consolidation. Fine. We'll see one small similar problem to your assignment in a direct shear test. Okay, in a direct shear test. So that's all with consolidation. Okay, we are going to find root t. We are the main parameter that we are finding is going to be cv value, which is going to be constant, and that can be related to the soil in the field also. Soil field, the field soil also will have the same cv value, which is taken as constant. And we find another important parameter is going to be cc. Okay, so CV and CC are the two important parameters that we get from our consolidation test. Fine. So in a direct shear test that is conducted on a dry sand, okay, whenever it gives dry sand, you have to take C as 0, okay, or pure sand. Okay, so test on dry sand is conducted. The shear stress is 62 kilopascal and the normal stress is 100 kilopascal. Find out the angle of internal friction. So if you remember the equation, that is nothing but for direct shear, it is tau equal to C plus sigma tan phi. Okay, so this is the formula. So it is given as dry sand, so your C is 0. Tau is your shear stress, so shear stress equal to sigma is your normal stress, tan phi. Okay, so can't you find phi from here? So your tan phi is 62 by 100. So your phi is tan inverse of 62 by 100, which is going to be 31 degrees. So there is a similar problem in your assignment, where you can use the same formula. Okay, tau is nothing but shear stress, sigma is a normal stress. Whenever it is given dry sand or cohesionless soil, pure sand, okay, you have to take C as 0. Okay, sigma tan phi is given, so from that we can find out what is the value of sigma. Okay, so fine. I have come to the end of the session. Stop presenting. Okay, so anyone have any doubts? I didn't turn on my video, did I? So is there any doubts? I have activated turn on your microphone. So this is your last class, I believe. You have any doubts so far in the topics taken in calculation part or anything?